The clock reads 3:18 p.m. on February 27, 2026, at the Jet Propulsion Laboratory in Pasadena, California. In the quiet hum of Building 264, a trajectory analyst sits at her workstation running routine updates on a predictive orbital model. This task is one she has repeated countless times since the summer. But today, something different happens. New observational data arrives from the Global Telescope Network, and as she integrates it into the system, the model doesn't behave as expected. Rather than refining the object's predicted path, it continues moving in the same direction toward a boundary. This object, known as 32 Atlas, has been on her radar for a while, and she's been monitoring it closely ever since it first appeared in the dataset. With the new data, she pulls up the previous revision and overlays it against the latest one. What she sees is alarming: two separate data points from two distinct observation windows, both showing the object edging closer to the outer limits of Jupiter's gravitational influence. She leans back in her chair, not in shock, but in quiet realization. It's that moment when numbers reveal something the model never predicted. She calls the senior analyst, who pulls up the same data overlay. The two of them sit in silence for 11 seconds, both absorbing the significance of what they've just seen. Finally, the senior analyst instructs her to run the outgassing correction once again to rule out the possibility of a modeling artifact. She runs the correction, but when the results come back, the object still edges measurably closer to Jupiter's Hill sphere than the model had ever predicted. This isn't just a flyby, it's an encounter that is rapidly evolving. The senior analyst asks her to check the calendar, not to call anyone else, but to confirm an unavoidable truth. There are only 18 days left before this encounter passes a critical point where further observation will be impossible. After March 16th, 32 Atlas will move beyond the observational range of every instrument on Earth, including those in orbit. From that point on, the data from this object will be gone forever. This moment marks a critical turning point. This isn't just a story about an interstellar object passing through the solar system. It's a forensic investigation of a closing window, an analysis of how physics is about to impose its will on 32 Atlas. As the analyst reflects on the path the object is taking, the realization sets in that soon all questions will become permanent answers. Once this window closes, the data set will be locked forever. Before diving into the mechanics of this situation, let's break down what is happening with 32 Atlas. Orbital prediction is not just about guessing a path, it's about precise calculations, adjustments, and corrections based on years of data. Scientists build an ephemeris, a table of predicted positions using every piece of observational data they can gather. The more accurate the data, the more refined the model. A single adjustment to the model is routine, but two refinements pointing toward the same boundary show that something significant is happening. It's not just a change, it's a pattern that could unlock something profound about the object's trajectory. The first refinement comes from the global network of over 200 observatories spread across multiple continents. They have tracked 32 Atlas with the largest coordinated effort ever for an interstellar object. When that data is integrated, it shifts the predicted path slightly closer to Jupiter's gravitational zone. Scientists take note of it but continue their routine observations. As 32 Atlas passes through the inner solar system, spacecraft instruments near Mars capture imaging data that surpasses the capabilities of any ground-based telescopes. These spacecraft bypass Earth's atmospheric constraints, allowing for far more precise observations. The integration of this data shifts the trajectory once again. The path continues in the same direction, always toward the same boundary. Jupiter's Hill Sphere. This zone is a critical threshold. It marks the region where Jupiter's gravity becomes the dominant force, overpowering the Sun's gravitational influence. For the largest planet in our solar system, this boundary extends roughly 53 million kilometers from its center. This boundary is not just a line on a map. It is a profound demarcation where the gravitational forces acting on 32 Atlas will shift from the Sun's influence to Jupiter's. As the object nears this threshold, Jupiter will become an active participant in this encounter, not just a backdrop. In orbital mechanics, the impact of this shift is monumental. At this distance, the tidal forces Jupiter exerts on 32 Atlas will start to stretch and stress the object. The force will be stronger on the side of 32 Atlas facing Jupiter and weaker on the opposite side, creating a differential pull. For 32 Atlas, a 2.66 kilometer nucleus, this is not a hypothetical scenario. This is real mechanical stress being applied to an object that weighs 40 times more than the asteroid 2I, Boros, moving through the gravitational field of a planet that is 318 times the mass of Earth. How 32 Atlas will react to these forces remains uncertain. Scientists don't fully understand its internal composition, which adds another layer of complexity to this encounter. As we move forward in this story, the challenges grow more apparent. We are witnessing a boundary that marks the moment when science can no longer theorize. The situation is turning physical, and it's a situation with very real consequences. How 32 Atlas reacts to Jupiter's gravitational influence will shape the future understanding of interstellar objects. These moments, however, are fleeting. Once the object passes the Hill sphere, we will never have a chance to observe it again. This narrowing window forces humanity to confront more than just the limits of our models. It challenges the very infrastructure that governs how we respond to cosmic events. The universe does not wait for bureaucracy. As March 16th draws closer, 32 Atlas accelerates toward its encounter with Jupiter, and our window for observation is slipping away. What happens next will have profound implications for how we prepare for future cosmic visitors. As 32 Atlas continues its trajectory toward Jupiter's Hill sphere, the clock is ticking and the pressure is mounting. The Juno spacecraft, already in orbit around Jupiter since 2016, is ideally positioned to gather crucial data during the object's flyby. Juno is equipped with an array of sophisticated instruments, including a visible light imager, an infrared mapper, and radio and plasma wave sensors, exactly the tools needed to study the object in exquisite detail. These instruments could have revealed critical information about 32 Atlas's nucleus morphology, the composition of its jets, its electromagnetic signatures, and even the potential for fragmentation. Juno was ready, its position was perfect, the science case for the targeted redirection was sound and peer-reviewed. The delta maneuver required to adjust its trajectory was within operational limits, and the need for this observation was irreplaceable. All the pieces were in place to capture unprecedented data about this fleeting visitor from interstellar space. Yet, within 48 hours, the proposal to reorient Juno to observe 32 Atlas was rejected. Fuel reserves and mission priorities were cited as reasons for the rejection. On paper, it made sense. Juno's mission was primarily focused on studying Jupiter itself, and diverting its attention to 32 Atlas could have compromised other key objectives. The technical justification, according to the decision-makers, didn't survive scrutiny. However, the result of this decision is starkly clear. The one spacecraft perfectly positioned to observe this event was not redirected in time. Juno, with all its scientific capabilities, would not capture the data that could have answered some of the most pressing questions about 32 Atlas. The window for observation closed, and the opportunity slipped away. In science, timing is everything. The rejection of the proposal reveals a deeper issue. It's not a failure of scientific understanding, but a failure in the speed at which decisions are made within institutional frameworks. The universe operates on its own timeline, moving at a pace that doesn't wait for the bureaucracy of scientific committees. In this case, the universe didn't wait for Juno to reposition, and the result is irreversible. The encounter with 32 Atlas has highlighted a significant gap between scientific potential and institutional agility. This missed opportunity, however, is not just a failure of one mission. It serves as a case study for how humanity is structured to respond to cosmic events. The next decade promises an increase in the detection of interstellar objects, and with it, more narrow, non-renewable observation windows. The Vera Rubin Observatory, with its unprecedented sky coverage and rapid survey cadence, will significantly increase the detection rate for interstellar visitors. But the same challenge will persist. Detecting an object is only the first step. The real test lies in how quickly we can act when the universe presents an opportunity. For 32 Atlas, the decision-making process was too slow. The operational window was measured in days, while the review cycles of institutional processes take weeks. As a result, the most capable observational asset within range of this historic event was left unused during the critical moment. The consequences of this delay will be felt for years to come, as the data that could have been captured is now permanently out of reach. The questions left unanswered are now etched into the record, forever lost to time. As we move forward, the implications of this event go beyond just one missed observation. They expose a structural problem in how we approach rapid response situations in space science. The missed opportunity with Juno serves as a cautionary tale for future interstellar encounters. We must rethink how we structure our decision-making processes, how we allocate resources, and how we prepare spacecraft for these once-in-a-lifetime events. Time is the one resource that cannot be replenished, and when it's gone, so too are the opportunities it holds. In the next section, we'll explore the broader implications of this encounter. 32 Atlas is more than just an interstellar object passing through our solar system. It's a test of humanity's readiness to act at the pace required by the universe. This encounter exposes not only the technical limitations of our current infrastructure, but also the institutional and structural barriers that prevent us from acting swiftly. We'll dive deeper into the consequences of this failure and what it means for our future interactions with the cosmos. Looking beyond the immediate failure with Juno, we must confront the larger lesson that 32 Atlas teaches us. This is not just a story about one missed observation. It's a reflection of our current place in the grand cosmic scale. A Type 2 civilization, as theorized by physicist Michio Kaku, would be one capable of harnessing energy on the scale of entire star systems. Such a civilization would never miss an observational window because their infrastructure would be designed to act at the speed of opportunity. For them, these fleeting cosmic events would be captured in real time, with no delays or bureaucratic red tape to slow them down. Humanity, however, is not yet a Type 2 civilization. We are still in the early stages of our technological evolution. While we are capable of detecting, tracking, and predicting the movements of objects like 32 Atlas, we are not yet equipped to act quickly enough when the universe offers a fleeting opportunity. This is the gap that 32 Atlas has exposed. We have the technology to observe and understand, but our institutional structures and decision-making processes are not yet agile enough to keep pace with the cosmos. In practical terms, this means that every future interstellar encounter will be judged against the benchmark set by 32 Atlas. The lessons learned from this event, both the successes and the failures, will shape how we prepare for the next wave of interstellar visitors. As the Vera Rubin Observatory and other next-generation survey instruments increase the detection rate of interstellar objects, we must be ready to respond faster. The physics of the universe moves quickly, and our systems must evolve to match that pace. One of the most significant takeaways from this encounter is the importance of flexibility in our decision-making frameworks. In the case of 32 Atlas, the critical decision was whether or not to redirect Juno to capture the object during its closest approach. The decision was made too slowly, and as a result, we missed an opportunity that will never come again. Future missions must incorporate more flexibility into their operational procedures. Spacecraft should be equipped with pre-positioned fuel reserves, and rapid response protocols should be established to ensure that observation windows are not missed. 32 Atlas serves as a stark reminder that the universe does not wait for us. It offers fleeting opportunities, and if we are not prepared to act quickly, those opportunities will be lost forever. The next interstellar object may not give us months of warning. It may not give us years to prepare. We must be ready to respond immediately or risk missing another chance to unlock the secrets of the cosmos. In the following section, we will delve into the long-term consequences of the 32 Atlas encounter. The missed observation has far-reaching implications that extend beyond just this one object. It calls into question how we structure our space missions and how we prioritize resources when the universe presents an urgent, non-renewable opportunity. The future of interstellar exploration depends on our ability to adapt and act swiftly when the cosmos demands it. As we reflect on the missed opportunity with 32 Atlas, it's essential to consider the broader implications for humanity's future in space exploration. The universe is full of objects that pass through our solar system, some of which may offer crucial insights into the origins of life, the nature of interstellar matter, and the dynamics of far-off star systems. These objects are rare and offer a once-in-a-lifetime opportunity to expand our understanding of the universe. Yet, if we are not prepared to act swiftly, we may miss these moments forever. 32 Atlas has highlighted a critical flaw in our approach to space exploration: the mismatch between the speed of discovery and the pace of our decision-making. As the detection rate for interstellar objects increases, so too does the need for a faster, more responsive approach to observation and data collection. The failure to redirect Juno in time serves as a case study for how we must evolve our systems to meet the challenges of the future. One possible solution lies in the development of a more agile decision-making framework for space missions. This could involve creating pre-approved plans for how spacecraft should respond to unexpected encounters with interstellar objects. By streamlining the approval process and establishing rapid response protocols, we can ensure that we are ready to act when the universe offers its fleeting opportunities. Another key lesson from 32 Atlas is the importance of resource allocation. In this case, the decision not to redirect Juno was based on fuel reserves and mission priorities. While these factors are important, they must be balanced against the value of the scientific opportunity at hand. In the future, space missions should be designed with flexibility in mind, ensuring that spacecraft have the necessary resources to adjust their trajectories and capture critical data when the need arises. As we look to the future, the 32 Atlas encounter will serve as a benchmark for how we approach interstellar exploration. The next interstellar visitor may not give us months to prepare. It may not give us any warning at all. We must be ready to respond immediately with the right tools and the right infrastructure in place, to ensure that we do not miss another opportunity to explore the cosmos. In the next section, we will discuss how the lessons learned from 32 Atlas can be applied to future space missions. By adapting our decision-making processes, prioritizing flexibility, and preparing for the unexpected, we can ensure that humanity is ready for whatever the universe throws our way. The 32 Atlas encounter marks a pivotal moment in humanity's journey into space exploration. While we may have missed an opportunity to capture valuable data from this interstellar visitor, the lessons learned from this experience will shape the future of interstellar exploration. As technology advances and the detection of interstellar objects becomes more frequent, the question will no longer be whether we can detect these objects, but whether we can act quickly enough to study them in detail before they slip beyond our reach. One of the most critical changes that must take place is a shift in how we structure our space missions and decision-making processes. As the 32 Atlas encounter has shown, we cannot afford to wait for weeks or even days to make critical decisions. We need to develop rapid response systems that can react in real time to cosmic events. This means equipping spacecraft with the necessary resources to make adjustments on the fly, streamlining approval processes, and creating protocols that allow us to move at the pace of the universe. Moreover, the future of interstellar exploration depends on our ability to coordinate and collaborate on a global scale. The 32 Atlas mission was a global effort, with over 200 observatories tracking the object across multiple continents. This coordinated effort is crucial as the rate of interstellar detections increases. However, it is not enough to just observe and track these objects. We must be ready to act when the opportunity arises. This requires a new level of international cooperation, with a shared understanding of the importance of rapid response and the need for flexible, adaptive strategies. The Vera Rubin Observatory, with its unprecedented sky coverage and rapid survey cadence, will play a pivotal role in detecting future interstellar visitors. But as we've seen with 32 Atlas, detection alone is not enough. We need to be able to act quickly to capture critical data before the window closes. This will require a fundamental shift in how we approach space exploration, from a system designed for slow, deliberative decision-making to one that is agile, responsive, and prepared to meet the challenges of the cosmos. Looking forward, we must also consider the ethical and philosophical implications of our readiness or lack thereof. As a civilization, we are on the precipice of a new era in space exploration. The next decade will bring more interstellar objects into our solar system, and with them, more opportunities to learn about the universe. How we respond to these opportunities will define our place in the cosmic timeline. The lessons learned from 32 Atlas must guide us as we prepare for the next wave of interstellar visitors. In the final section, we will take a closer look at how we can apply these lessons to future space missions and ensure that humanity is ready to capture the next great cosmic opportunity. As we conclude this reflection on the 32 Atlas encounter, it's clear that the event has left an indelible mark on humanity's approach to space exploration. The missed opportunity to redirect Juno and capture critical data from this interstellar object has revealed a systemic problem in how we respond to time-sensitive cosmic events. The lessons learned from this experience are not just technical, they are fundamentally philosophical and systemic. Future interstellar encounters will provide similar challenges, but with one significant advantage: we now have a concrete example of where we went wrong. The 32 Atlas encounter has highlighted the gap between our technological capabilities and our institutional response times. As we look to the future, we must prioritize agility, flexibility, and rapid decision-making in our space missions. This means reevaluating how we structure mission proposals, how we allocate resources, and how we ensure that spacecraft are equipped to respond to unexpected cosmic events. The future of interstellar exploration will require a new level of collaboration and coordination on a global scale. The 32 Atlas mission has shown us that no single nation or institution can tackle these challenges alone. We must work together, share resources, and create a collective strategy for responding to the cosmos. This is the only way to ensure that humanity is ready for whatever the universe throws our way. Finally, the 32 Atlas encounters serves as a mirror, reflecting both our progress and our limitations. It has shown us how far we've come in terms of detecting and tracking interstellar objects, but it has also revealed the significant gaps in our ability to act when the universe presents a fleeting opportunity. If we are to succeed in the next chapter of space exploration, we must take these lessons to heart and ensure that we are ready to respond at the speed of the cosmos. The window for observation may be narrow, but the lessons we take from these experiences will shape the future of humanity in space. As we prepare for the next interstellar visitor, let us learn from the mistakes of 32 Atlas and ensure that we are ready to capture every moment the universe offers. Don't miss a single opportunity to learn from the cosmos. Subscribe and stay updated for more stories about our place in the universe.